Let's get started. So I just want to give you a summary of what's going to happen for the next few classes. We are going to have, so we have finished the main arc of the theory for now. I want to talk about a few topics. And to do that, we are going to have guest lectures. Um, uh, this week, Litu is going to be talking about sort of posterior sampling algorithms for today and possibly on Thursday as well. Next week, then we want to come back to some theory, the recent theory. So we have talked about posterior sampling algorithms, and very often you have seen that it's either the dimensional dependence is really bad, or you will need to do certain approximations, which is what he's going to talk about today to get things to work at scale. So we'll come back and talk about the theory of that. And so next week, Advait is going to talk about some recent work on smooth analysis for posterior sampling, as well as hardness of posterior sampling, recent papers in that space. So that's basically what's going to happen next week. And then I'll come back and do discrete diffusion. So I'll start both the discrete flow matching versus sort of mass diffusion language models, Gaussian models, and all that. So I'll go through maybe 3 or 4 lectures on just discrete diffusion. And then we'll close with a couple of guest lectures by researchers from DeepMind and other things. So that's the arc of the rest of it. So today and possibly Thursday, Litu Rout, he's a PhD student here, and he's going to be talking about some of his work on inverse problems. Litu?
Yeah. Hi, everyone. Can everybody hear me okay, or should I be louder? It's fine. Okay. So I'm a PhD student in the UC department, co-advised by Professor Sanjay Shakatai and Professor Konstantin Karmanis. So today in this class, we're going to talk about how to solve inverse problems using latent diffusion models. So let's get started. So let me start with a brief introduction to general inverse problems. So in general inverse problems, we have a ground truth image that is shown here on the left-hand side. So we are going to model the imaging pipeline through some imaging system, and then the noise in the measurement, we are going to model that by this operation. And then finally, once the ground truth image goes through this imaging pipeline, we obtain something what we call the measurements. Now our goal is that given these measurements, we would like to reconstruct the ground truth image, and we want to find one possible such images. Okay. So as you may know, so this problem is ill-posed. What this means is we may be able to find, we will be able to find there are so many matrices of same shape and size as that of the ground truth image, which when we pass through the imaging pipeline will satisfy the measurement constraint that we have. But these matrices may not even look like realistic. They may not look like a real image. It could just look like some random noise or something like that. But as long as it satisfies the measurements, we won't be able to detect them. So that's why this problem is ill-posed. There are infinitely many such solutions that you can find. So to get rid of those unrealistic samples, we're going to specify something what we call this prior. So we will define some properties of the matrices that we're looking for. Not any matrix, we're looking for some matrices which will satisfy some prior knowledge that we are going to enforce. Okay, so we can just say that we're looking for a matrix which has low total variation, or some matrix which can be generated by some generative model. Okay, so we're going to specify some properties that we're looking for. So that's essentially the problem setting. So let's look at some of the examples of inverse problems. So one example here, as you can see on the top left, is the freeform inpainting, where the input image has several pixels missing, and our goal is to inpaint those missing pixels. Okay, so that's called freeform inpainting, and this is not just some canonical example. You can in fact see these problems occurring in real world. For example, if your mobile phone camera, let's say, or the sensor that you have in some complex imaging system, if the sensor is exposed for a longer time, then you'll acquire too many photons within that short span of time, and your intensity will be saturated. So in that case, the true intensity that you are supposed to capture will not be captured by your sensor, it will be saturated. So you can remove those pixels and try to infill that using some algorithms. Okay, so this is one case where you see such type of problems in reality. For some other examples include, like, you have some photograph, some ink got like spilled over, and then something is covered, and then you can replace that with some mask, and then you can inpaint that using your algorithm. So these are some of the examples where you see these problems in real world. Another example is motion deblur. So in this case, the ground truth image goes through some motion blur kernel, and you observe like a blurred version of the image. So this is what you observe. These are your measurements. Now, given this, we would like to reconstruct the underlying ground truth image. So that's essentially the problem. So now, where do we encounter such problems in real world? We encounter such problems when you, for example, you are trying to take a picture on a moving vehicle. So in that case, you'll see that the image that you acquire will have some kind of motion blur due to the movement of the platform on which you're taking the image. Another example includes like when you're taking, let's say, a selfie using your hand. If your hand is not steady, then also the image that you'll acquire will have some kind of blur due to your movement of the hand that you have. So these are some of the cases where you see these problems, and we wish that we could go back in time and again take the image from a static platform. But that is not possible because the time has already passed. You cannot go back and retake the image from a static platform. So now the question is, what else can you do? So we rely on some software solution instead of asking to retake the image by going back in time, which is not feasible. Then there is this another class of inverse problems for example, super resolution, where the input image is a low resolution version of the object that you want to acquire. And in this case, we want to improve the quality of the input image. So you can think of that you are taking an image using, let's say, some Android phone camera, and you want to convert it to some iPhone camera. So you have so many pixels representing the same spatial region. So for example, let's say in this classroom, there are 20 chairs in each row, and there are 20 such rows. So we have total a 20 by 20 grid. Now, if you want to take a picture from the rooftop here, and each pixel, let's say, represents 4 chairs, 4 by 4 chairs. So in that case, 4 chairs will be integrated to give you a single pixel. So in that image, you will not be able to resolve between 2 different chairs, adjacent chairs, right? So what you would have liked instead is to have a single pixel representing each chair individually. That way you can resolve all of us separately, right? So that's what I mean by a high resolution camera versus a low resolution. Yeah.
In that example, the resolution of the fire is built up.
Which resolution?
The fire distribution built up.
Yeah, so the high resolution. So you assume that you have some model which knows how high resolution images look like, and the only thing you observe is a low resolution image. Okay, so these are the two things you assume. Then you have another example, Gaussian deblur, where the input image is this one, the ground truth image that goes through the imaging system, and you observe this blur kernel. Here, the forward process is like a Gaussian blur. So you convert the image with a Gaussian blur kernel, and that's what you see as your input. Now, given this, we want to go back to the ground truth. Now, where do we see such type of blur in reality? So you see such blurs when you are like building the sensor. If the lens of the optical lens is not aligning all the light rays to it's not focusing at the same point, they're like shifted a little bit, then it will reflect as like a blur. And because when light goes through the lens, you can model that as a convolution operator, and that is how you'll see these issues in reality. So then our goal, the image that you'll obtain will not be as sharp, because the point's light rays are not focused at the same point. So they're shifted a little bit. And that blur you can model by this Gaussian convolution, and we want to unblur it. That's essentially our problem. Okay, so these are some of the examples of general inverse problems that we'll discuss today. Okay, coming to the solution. So we discussed the problem statement and some examples of inverse problems. So now, what are the typical solutions that people have studied in literature so far? So you can divide the solutions into mostly like 2 methods, 2 classes. One is this supervised method, and another one is the unsupervised methods. So in the supervised class of methods, what you do, you prepare a paired set of training examples. For example, you assume that you have access to a set of samples from some data distribution. You take those samples and you mask out some portion of it. So now you have your input and the corresponding output, and then you can take a neural network and try to learn solve this regression problem. You feed this image as input to your neural network. The network will predict some high resolution image or some cleaned image which may not look like this ground truth image. You compute the error, backpropagate to update the parameters of your model. So now again, for this one, you need to have a paired set of examples and a neural network trained on those examples. Now, if you want to change the task from box inpainting to random inpainting,
Same box, or can I train it?
random, you can have the box at random locations. Yeah. Depending on what you have in your inference time, if your box is always centered, then you can prepare the data where the input is always centered. But if your inference time, you can just, yeah. Yeah, yeah. And then for random inpainting, you can just prepare again another set of paired examples. You take the ground truth image, you randomly mask some pixels, okay? And then you feed that as input to your model and you learn a new neural network.
But like the panda example that you showed
Yeah,
before,
yeah.
that was not a shape that you wouldn't want to do it for all possible shapes.
Yeah. So you can just randomize the masking. So you can
that
just,
would be fine.
that will be fine. So you can generalize to such inpainting things, yeah. And then for motion debuller, similarly, you can take some images and then you can prepare the input and then train a neural network to learn the mapping between input and output for all these tasks. So now in this case, if you notice, we need two things. First is that we need to have a paired set of training examples. And the second is you need to have a model for each task. And this is something which is very difficult to do because you don't know a priori what the users like are going to test your model on. They may test it on super resolution, or maybe it will be a mixture of all of these things. You don't know what is the type of blur that you have. So in those cases, that's why it's a difficult thing to just pre-train on a certain task and then deploy it. Because if you train a model on a particular task and you deploy it, and then the users test it on a different task, then it won't work, and then it's a problem, okay? So the other class of methods called unsupervised methods. So here you don't train a model for every task. You use the same model and you'll be able to solve all these inverse tasks using just the same model. For example, here you have a generative model, you have a prior, you just specify some properties of high resolution images. Then you can design efficient sampling algorithms instead of designing efficient training algorithms. You just design efficient sampling algorithms to solve inverse problems. Like here you can do block in painting, here you can do like freeform in painting, and here it's like extreme random in painting. So 90% of the pixels here are masked, and just 10% pixels, given that you will be able to reconstruct some of them to some realistic image. It may not be the true underlying ground truth image, but it is a real image because it comes from the prior. Okay. Similarly, here you have a grayscale image, you can convert it to some color image, and these are some of the applications that you can do by designing efficient sampling algorithms instead of having to retrain a model for each task. Okay, so there is no training involved. So you can solve like many inverse problems using the same generative prior. So for these reasons, unsupervised methods have become quite popular. And there are some other advantages of using the unsupervised methods, which you have listed here. The first thing is that it's easy to train a generative model on almost all images on the internet. But if you have to annotate the images for each input-output pairs, then it's a difficult thing to do. But you can just scrap everything from the internet, train a generative model on that. That's easy, and people have already done that. So you can just look at these models, train on like almost everything on the internet, and it's easy to train because it doesn't require any annotation. And the second thing is that you don't have to retrain this base model for each task. So you don't need any expensive retraining per box in painting or random in painting as you would require for the supervised methods. And you do not need any paired input-output samples. Okay, so you just need the base generative prior and then design some posterior sampling algorithm. So these are two advantages of using the unsupervised methods. And the third one is you don't have to, like somebody has already spent a lot of data and compute to train these foundation models at scale. So you don't have to reinvent everything again. So you can just leverage the pre-trained model and just convert it to some posterior sampling algorithms without outside training. And then final thing is posterior. So if you solve this using supervised methods, what happens is the optimal solution you'll get is going to be the mean over the possible outcomes. So what I mean by that, if you give a low resolution image input, there could be many high resolution images which will lead to the same input or same measurement. Okay, so the supervised method will converge to a solution which is the average over all possible outputs, high resolution images. So that way the solution you will get will be some kind of blur, so it will be at the edges you will have some mismatch there. And this is why it's not really, if you look at the real outputs of a supervised method, it looks blurry. It's not a real sample, it's the average over many high resolution images. So that looks something like this. So for a given low resolution image, if you so this is, for example, a low resolution image. And if you use the MSE based, okay, so you have a low resolution input image, MSE based solution will converge to something which is the average over all possible high res images. Okay, but if you're using some posterior sampling algorithms, it's going to pick one of these high res images. So that's, for example, let's say GAN chooses this one. So this is from some SR GAN paper, you can check it there. And over the years, there are several generative models that people have come up with, and you can use all the generative models as priors for solving inverse problems. There are various null autoencoders, GANs, and most recently, diffusion models have emerged as the powerful prior for solving inverse problems. Okay, so they give you some idea about like what properties the underlying matrices should satisfy. You can get a good sense of it from the diffusion priors. Okay, in today's lecture, we are going to focus on diffusion as a prior for solving these inverse problems. So let me start with a quick introduction to this diffusion model so that we understand the notations. We have already gone over this in the previous lectures, but for the sake of the notations, let me just like give a quick recap of this one. So as you know, the diffusion models have two processes. There is a forward process that starts with a clean image, and then you gradually add noise to it, and then eventually you converge to something which is pure noise. That's your forward process. And you can model the forward process through a stochastic differential equation with a certain drift and a diffusion coefficient. And then the reverse process is essentially the reversal of this forward STE, which is given by another stochastic differential equation. And the reverse process starts with pure noise, and then it gradually removes the noise from it. Eventually, you end up with a clean sample. So that's essentially the two processes we are dealing with. The forward, yeah. Yes, yes, yeah. So yeah, so you can choose f and g for anything you want. But if you choose this f of x for a particular value of this function, it becomes OU. So I'm going to go to the next slide. So if I choose my f of xt as only a function of the state, x and xt here, then and then the g of t, I choose that as independent of x, then it's the OU process. And this is the simpler one to implement. That's why like everybody relies on this one. It has some nice interesting properties that if you want to go from x0 to xt, you don't have to go from x0 to x1, 1 to 2, 2 to 3, and so on and so forth. You can just directly jump from x0 to xt because it has some closed-up solution to this one. And so that's why like, people use this, choose this f and g such that it becomes easy to simulate. Okay. Now for that choice of f and g, the reverse process again takes the following form. Okay, so now if you want to, at the end of the day, what we want to generate images from the real data distribution. So we don't have the forward process. We start from a noise and we want to be able to implement this reverse process. That's what we want to do. Now to implement this reverse process, as you see, we need some grad log pt of x, which we don't know. So that's essentially what you see here in the OU process as well. But that's why the third important step in these diffusion models is to use a neural network to approximate that grad log pt of xt. Now, if you know, if you can train a neural network to approximate this grad log pt of xt, then we know how to simulate this ST. We can use some popular discretization, Euler-Maruyama or some other discretization, and we can simulate this reverse process. Okay. So now the only thing that is remaining to discuss here is how do you train a neural network to approximate this grad log pt of xt. So the forward process, there is nothing to learn. The reverse process is defined by when you specify the forward, the reverse process is essentially you just align the marginals and then you can derive that one. And for each reverse process, we need to have this one in order to simulate this. So that is the only unknown, and we can approximate that neural network.
In practice, am I just using off-the-shelf methods once I have my score?
Yeah.
Function?
Yeah, when you have the score function, you can, this is the actual thing. You can use any discretization which gives you the list.
But I mean, in practice, am I eating anything?
No.
Or just kind of like plugging it in and.
No, just plugging it in, nothing, yeah, yeah. Okay, so now the question that remains is how do you train a neural network to approximate that grad log pt of xt? That's the only part that is remaining. So to do that, you can use this tedious formula that goes back to somewhere in the 1950s. And this formula says that if you have a sample x0 drawn from some distribution, p0, and then you add some noise to it with some covariance sigma t, then you have some xt here. Now, given xt, if I ask you what is your best estimate of x0 that could have given me that xt, then I can compute the best estimate by this MMSE. The MMSE estimate is essentially the minimum mean square estimate for that one, and you can compute that explicitly using this formula. Okay, so that's essentially this 2D's formula. So here you see that if we want to compute the best guess for x0, that depends, that's essentially this, and it can be computed using only this xt. We don't need anything else. Xt and sigma t is anyway we already know. So if we know xt, we can just put that into this grad log pt of xt, and then we can compute the best guess here. So now this gives us a relation. You can just rearrange this expression to compute this grad log pt of xt as the expectation minus xt divided by sigma t square. Okay, so that's how you can actually figure out what is this grad log pt of xt. And that gives you something like, that's essentially is telling you that if you can find the minimum mean square estimate of this xt minus x0 square, then the solution of that is essentially going to be e of x0 given xt, and then that is going to be some function of that is going to give you the score, because e of x0 given x0 given xt minus xt divided by sigma t is your score. So you just have to use a neural network to give you x0 given xt. So input output pairs. You can just take some x0s, go to some xt, then you learn a neural network. So here with some parameters theta to learn a mapping between xt to x0. And the optimal solution of that is your MMSE estimate. And then given that, you can find the grad log pt of xt from it. Okay, so that's how you learn the score function. And once you, so this is again another formula, the theorem that gives this thing explicitly. So we want the score function s theta, the neural network, to approximate grad log pt of xt exactly. Okay, but this thing requires you to integrate over this xt marginals over that. But this is something intractable to compute because you do not know the distribution over x0. You only have some sample access to x0. So we cannot compute this distribution over xt's. But instead, you can, if you write this j2 of theta, another loss function, where you compute the expectation given x0 because you have some sample access to x0s, and then condition on x0, you know the distribution of xt given x0, because that essentially comes from something like this. If you know x0, epsilon is a Gaussian, so it's just p of xt given x0 is a shifted Gaussian with the mean shifted to x0, and the covariance is sigma squared, t squared. Okay, so you know how to compute this. You have some sample access from x0 distribution over x that, so you can easily compute this. So you use a neural network to approximate grad log pt of xt given x0 instead of using that to approximate this directly. Now the interesting thing about this theorem is that j2 of theta is, you can write that as j1 of theta plus some constant. Okay, so this says that the minimizer of my j1 theta, since this is constant independent of theta, so the minimizer of j1 theta and j2 theta will be the same. So instead of using this as a loss function and trying to use this, like optimize the parameters of your neural network to minimize this loss, you can optimize the parameters of your neural network to minimize this loss, which is practically implementable. Okay, and the solutions of both the things will be the same, so you really, you don't really lose anything. Okay, so this is how you can train a neural network to approximate grad log pt of xt, some version or some approximation of that. And once you have that, you can just plug that back into this expression, do some discretization. Now you have your generative model. You start from pure noise, you compute the drift, you discretize this dt into some del t. Brownian noise, you can just compute the Gaussian with some covariance and keep denoising one step at a time. Okay. All right, so that's a quick recap of this diffusion models, the forward and reverse process, how you train a neural network. So now I'll move on to solving posterior sampling using this diffusion model as a prior. So far, like if there is any questions on training or inference, I'll be happy to take. Are there any questions? Okay, okay, yeah.
This is like maybe obvious, but you're gonna learn this sport at a specific time.
Right, yes, yes.
Yeah, and then that's gonna fix the time stabilization.
Yes. Yes. Yeah. Okay, so now let's look at this posterior sampling using diffusion models as priors. So I'm going to talk about 3 papers here. So this diffusion posterior sampling is where it's a diffusion model where diffusion is happening in the pixel space. Then we will go to PSLD where diffusion is happening in the latent space. And how do you solve inverse problems or do posterior sampling using both latent diffusion and pixel space diffusion. Then the final thing is that both DPS and PSLD, although they solve this posterior sampling using the diffusion either in the pixel or the image space, they all can be formulated as a first order approximation of something we will discuss later. It's a first order approximation. And if similarly, PSLD is also a first order 2D approximation happening in the latent space. Now, if you increase this order of approximation to a first or second order, you can reduce this approximation error. We'll talk about that also in the subsequent slides. So this is pixel space, this is latent space, and this is correcting the bias due to the first order approximation. So let's start with DPS first. All right, so let's set up the notations again. So as we discussed earlier, so the ground truth image here, we are going to denote them by x0, which is a sample from the data distribution. And then the imaging system, we're denoting that by A, some noise N. And then the measurements that we have, we'll just denote that by y equal to ax0 plus sigma y of n. So depending on what this A is, if it is a linear operator, we call them as the linear inverse problems. If A is a nonlinear operator, we call that as a nonlinear inverse problem. So now, as discussed earlier, so we only have access to y, and we want to find some x0 that satisfies this property, and also it satisfies the prior that we'll be specifying through some generative model. And the problem is ill-posed. What we mean by that is there are many such x0. So if I take some other x0 and pass this through this equation, I'll get same y. For many x01, x02, there are so many such x0s. If I put them into this equation, I'll get the same y. Okay, so that's why this problem is ill-posed. But we don't want any of those x0s. We want the x0s which satisfy some prior knowledge. Okay, that is specified through this. So these are the constraints that we have. Okay. So now let's again revisit the reverse ST that we looked at. So we had this dxt equal to minus xt minus 2 grad log pt of xt. There was no y. If you want to do unconditional generation, you just simulate this ST, but this thing you can just replace with, so this you just replace with grad log pt of xt. Okay, so this is what we had before. If you remove this and put this in, then we know that simulating this reverse ST will lead to some samples from this one, P0 dot. Okay, so that's what we will get eventually. So now if we want to do posterior sampling, we don't want to sample from P0 dot here. We want to sample from P0 this given some measurements that we know. Okay, so to do that, we need the score corresponding to that equation. So here, that's what you see here, pt of xt given y. But unfortunately, we do not have a neural network to approximate this grad log pt of xt given y. We have a black box neural network that is approximating only this grad log pt of xt. But what we want instead is a neural network that approximates this. So one way to solve this problem would be to retrain another neural network. So you just like draw samples from this, you noise them, and then you, again, the same way we train using the denoising score matching objective, then we'll get a new score function, another neural network. Okay, but that is expensive, but we don't want to do that. So interestingly, what you can do is, if you look at this expression, just by applying the base rule, the pt of xt given y, you can write this as y given xt times xt divided by y, and then log trig you can just do here, and taking the gradient of both sides, you see that this term here is independent of xt, and these gradients are taken with respect to xt. So this thing just goes away. So then this grad log pt of xt given y, you can replace that as with grad log pt of y given xt minus grad log pt of xt. Okay, so this is what we want. We don't know how to compute this, but we can break this thing without doing any approximations. We could just rewrite this as sum of these two terms. Now the good thing is we already have a neural network approximating grad log pt of xt. So we could just reuse it instead of like retraining everything from scratch to directly approximate this. So we could reuse this S theta to approximate this. So now the only unknown quantity in my reverse STE is this one. So now we have reduced the difficulty of the problem from approximating to directly grad log pt of xt given y to approximating grad log pt of y given xt. Okay, this is like an easier approximation compared to retraining everything from scratch. Okay, all right. So now the question is, how well can you approximate this? If you have a better approximation, then you'll get better results. So that's where all the difficulty now lies. So we'll talk about how some of the approximation in today's class. So let's get into that. So the reverse STE, if you notice, so here the time goes from t to 0. So I'm going to now switch the notation so that it becomes more convenient to understand. So time always goes forward. So it's like it's a little bit unconventional to think of it as t going from capital T to 0. So I just make this following substitution. I replace ut with xt minus t, capital T minus little t. And with this substitution, so I can just do that for all these things. And then my t will go from 0 to capital T. And then with that, like I have a new variable here, ut. So with this process now, the problem becomes how well can we approximate this quantity? It's just like some change of notation, but it's the same thing. Okay. Okay, so now the question is, so what is the difficulty here? So when we are simulating the reverse process, we start from pure noise, and then at every time step, we compute this drift and the diffusion coefficients. Then we go one step at a time. So suppose we are at time yt, we need, to compute the drift, we need to be able to compute this function, this gradient. Okay, so ut here is like a vector, and log p of things is a scalar, gradient of that is again another vector. So we should be able to compute this and add or something. And to compute this, we do not know how to compute this function because we don't have access to this function at this time. But what we know instead is that we can compute the function as when we have ut. Okay, so all we have to do is we just simulate this process all the way, get some ut, and we have access to this function because we know the given a clean image, we can just pass it through our imaging pipeline and extract some measurements, and we can compare with the measurements that we have. Because we know that y is some a of ut plus some sigma y of noise, okay, epsilon. So this is what we know. We don't know what is the measurement given a noisy image. Okay, so that's why we can only compute this at the end of the process, but we haven't reached there yet. So that's why the problem is difficult. Okay, so we are at time t, we want to compute this, but we need to compute this. We can only compute something which is in the future. We haven't reached there yet. And we have reached there yet, then we can change the process to resample again. Okay, so that's the difficulty here. So now the question is, before you actually visit to the end of the process, can you make some corrections to the current state so that at the end of it, you will have this higher probability of y given ut? Okay, so that's essentially the problem. So now how do you do that? Yeah, question. Yeah. Yes, yeah, you have access to A. No, you have always, you assume, so here we're assuming that we have access to A, the measurement operator. That's like, if I give you a clean image, you can just mask out half of it and you know that A, right, operator. So that's easy. But you need to have a clean image in order to do that. Now, for example, if you want to do super resolution, if I give a high resolution image, you can just downscale it to extract the low resolution version of it. But if I give you a noisy image, then downscaling that will not give you the measurement. You'll get a noisy low res image, which is not what you have. You cannot compare that with the measurements that you have. Yes, you have A, you know this function, you know how to compute this. Like I said, this y, this thing is essentially proportional to something. Y, we know that A of ut plus some sigma t of epsilon. We know this. We know A, we know some noise, whatever, and we can compute this.
If I wanted, at least in principle, to do the hard quantity, I
Yeah.
have to have like the universe of different
UTs.
images
Yes.
that correspond to
Yes.
that particular
Perfect.
image.
Yes. Yeah.
And instead I'm picking one of them.
Yeah, then it's a bad thing. Yeah. Okay. So that's exactly the next slide. So essentially, so if you want to compute this probability, like you said, you have to compute the expectation of the function at the end of the process. So this is something you can compute at the end. So if you this is what you just said. So you start from ut, you run the process once. So you will, if I run the process once, I'm going to get some ut of 1. I run it again starting from the same point, I'm going to get ut of 2. I keep on running like that, so I'll get some ut of hundreds of those samples. Okay, for each of the samples, I know how to compute p0 of y given ut. I can compute this function, so I'll have a function of some p0 of y given ut of 1. Similarly, I'll compute for all of them. I just average them, and that's going to be my, I average these things, and that's what is going to be my true probability of y given ut. Okay, but this is, as you can see, I have to simulate this for, like, first of all, I need to have infinitely many such samples, to get a better estimate of the expectation. And the second thing is I have to do that for every time step, not just for this ut. I have to do that from here also. I have to simulate all the way. From the next time step also I have to simulate all the way. That's where, like, it becomes hard. Okay. So now the approximation that this DPS paper did is, instead of simulating this all the way and computing the expectation of the function, which seems to be hard, you can compute the expectation of this whole thing. Okay, so let's call that some variable, let's say ut bar, let's say. Okay, so this is just like compute the average of all of these. And that's what I'm going to denote by this quantity. And then we just compute that function once, ut bar. Okay, so I don't have to compute this function first of all for hundreds of samples. That's one advantage we get. And second advantage is that in order to compute UT bar, we do not need to simulate this 100 times or 1000 times and then average them. So 2D's formula we can use to directly compute UT bar given a single UT. Okay, so that's where, yeah. Yeah, we'll come to it, yeah.
One other, that you could just say, I'm gonna approximate the integral of the expectation of this on one sample.
Yeah.
Is that better? I just still
That's worse, yeah.
Still don't want to.
Yeah. Because that can, you can end up with a bad sample which is far from it, and the next iteration, it won't guarantee. Yeah, it's not even a sample, but it's just what these people did. I'm not saying this is the best thing to do, but I'm just saying like, this is what these guys did. This is just one way to do it, and this is what they did. But you are paying the price, like you said, it is some Jensen's gap here. Okay? Any questions?
So for each PV, how to sample, like, let's say 100 UT.
You-
For you, just one as well.
No, you have to do that if you were to compute this exactly. Then you have to follow these blue ones. Okay? You have to simulate many of those UTs, hundreds of them, compute that function for each of the sample you get, and then average them. Then you will be able to compute this exactly. This is the ground truth. This is the best you can do. It's the best. There is no approximation here, but it's expensive. But instead, what you can do, you don't have to simulate this all the way. 2D's formula tells you how to compute the average of all of these UT1 to UT100 without having to run the simulation. So you don't have to run the simulation from UT all the way to get 100 samples, then average them. 2D's formula gives you a formula to compute this UT bar as a function of UT itself. Okay, so that's where we will come next. So UT bar, you can compute as just like a function of UT. So you don't need to simulate this again and again to get UT bar. So that's why it's easy for them, because you don't have to rerun it again. For every time step, it's just one forward pass, and you are directly at the UT bar. And then once you have UT bar, you can pass it through this function. Then now you are saving like at multiple places. First thing is that you don't have to compute this function for many of these samples. And the second advantage is that you don't have to run the simulation. So two advantages we get under this approximation. So now, like Jacob was mentioning here, so you have, if you do this, this can be thought of as exchanging the expectation. So you want to compute the expectation of a function. Instead, what you are doing is you are computing the function at the expectation. You are evaluating the function at the expectation, and so you are. This is like the Jensen's gap, and this Jensen's gap can be like terrible. So that's under those cases, like you have to think of some other better approximation. Okay. All right. So there are some limitations of this approach. So here are some of the limitations. For example, when you use this pixel space approximation, as we saw here, this gradient of this gradient is with respect to UT, and UT is in the pixel space. So this log PT of thing is a scalar function. You are computing the partial derivative of the function with respect to each coordinate of UT. And if UT is in the pixel space, you have to take, depending on how many pixels you have to take those many partial derivatives. Okay? So essentially, that means that you have to compute the gradients in the pixel space. And if the size of the image is, let's say, 512 by 512, then you are like by 3, then you have to take like roughly 10 to the 5 partial derivatives, which can be expensive. Okay? And then the second drawback is that you need to have a generative prior for human faces if you want to solve inverse problems on human faces, which makes sense. You need a prior on human faces, you want to do posterior samples from that, so that makes sense. Now, if you want to solve inverse problems on cats and dogs, let's say from ImageNet, then you need a separate prior for that, okay, which kind of makes sense. But the issue here is that you cannot retrain this. You can only deploy one model at a time, let's say, in production, and you cannot change that based on the prior. So you need to be able to figure out a way to train almost on all these images, and then you should figure out how to extract the prior specific to a particular domain, instead of like having to retrain it in your domain. Because then if you want to train a model for each domain, you have to separate the data again for different classes, and you have to retrain a model for each class, and then again, you have to have different models for each prior, which is what we don't want to do. Okay? That's kind of like similar to what we did for the supervised methods, where we had to retrain a model for each task. Okay, here it's like you retrain a model for each prior, which we don't want to do. And then the third limitation is that if you deploy such models, then there will be some samples which are out of distribution. You do not know what the users are going to upload. In that case, your model will not generalize. So these are some of the limitations. And we try to overcome these limitations using some approach which we'll discuss next. So the question we ask is, can we use a general prior which is trained on both cats and dogs and human faces? So you have like a multimodal prior on different modes. And if you want to solve inverse problem on human faces, suppose this mode corresponds to human faces, then you can extract that prior from your generic prior, and then you can do inverse problems on that. You don't have to have a prior like this to do inverse problem. This is already integrated in your multimodal prior, and you can extract that. So how do you do that?
That's not, what's going to happen with DPS with multimodal prior?
You have to train it for all of that. That's essentially what you have to do. You have to train that model for a multimodal prior. Nothing will happen. You just have to retrain it for multimodal prior. Now, if you want, retrain the base diffusion model on like both this multimodal data set. You have to retrain it. And if you use DPS for this multimodal prior, first issue is that in the pixel space, these models.
This is like complexity.
Yes, yes. And the second issue is that we will discuss later that you don't, like the generated image may not come from the true distribution. Because the diffusion in the latent, so you have to go to the latent diffusion, first of all, to avoid the complexity in the pixel space. Once you go to the latent space, then it has some issues which we'll discuss next. We have some.
Yeah, but if I'm in complexity of
Yeah.
pixel space.
Yeah. Then you could train something on the multimodal data. Then you could just do the DPS. And you will have some error, some approximation, same Jensen's first order approximation.
That the most powerful
Models are latent. Yeah.
conceptual problem. It's
Yeah.
just that I don't have
Yeah.
multimodal prior
Yes.
in the pixel space
Yes.
because of complexity.
Yes, yes. Okay. So now how do you do that using latent diffusion? That's why the multimodal priors that are readily available, they are trained on like these multiple modes, but they're latent diffusion models. So how do you do DPS in the latent space? Okay, so because DPS requires you to have the measurement operator, P of y given x0, and you cannot compute that in the latent space, but diffusion is happening in the latent space. So we'll come to that formulation in the next few slides. So that's essentially the question we are asking. So how do you solve this problem using the latent diffusion models? And extract this domain-specific priors from this like multimodal prior that we have. Okay. So that's essentially, we solve that in the next paper, PSLD. So let's get to that. So in the DPS, the prior was a pixel space diffusion model where diffusion was happening in the pixel space. So you had this dog image, you were adding noise all in the image space. But now in the latent diffusion, so you take the image, you pass it through some encoder, you go to some latent space, which won't look like an image anymore, some latent structure. Then you add noise to the latent space. So diffusion here is happening in the latent space. And again, this is the forward process. You can do the reversal as usual. So you will just have to compute the score. You can train a neural network to approximate the scores, same as before. The only difference is that now the diffusion is happening in the latent space. And so if you, in the reverse process, what you'll do, you start from some noise, which is of the lower dimension as this one. Then you start denoising using the score function that you have. Then eventually you'll get some ZT, which is a clean sample. But this is not an image. Okay, so this thing you have to pass it through the decoder, then you will get an image. Okay, so now the DPS if you want to do, so this is essentially the reverse process. So this is the unknown quantity, same as before, but these are now in the latent space. So if you want to do DPS, we'll see like how that is done. But before you get there, now let's look at the complexity story here. So if you were to compute these gradients in the image space, you have to take the partial derivatives with respect to each pixel in the image space. And one example here is the stable diffusion V1.5, where X dimension could be like 512 by 512 by 3. So you need to take like roughly 10 to the 5 partial derivatives. But if you do the same thing in the latent space of this SD V1.5 is 64 by 64. So you have like much smaller number of partial derivatives to compute, so you can save some time. So that's essentially one benefit you get. Yeah. Yes, yes. Yeah. Always with respect to ZT. Here also is ZT, always. Yeah.
Plug in decoder of ZT.
Yeah, that's essentially the DPS thing. That's the next thing. So like you said, why don't we just like plug that decoder in here and then compute it? right? So you know how that this probability you can compute the expectation of this thing. So you take this ZT, pass it through a decoder, and then you just take the measurement. I can do that. So this thing works if your encoder and decoder are like one-to-one mappings. The problem is that in practice, the encoder decoder can mess things up because the encoder is operating as a compressor. So you can have multiple images, maybe realistic and unrealistic images, but when you compress them to the latent space, they will map to the same latent. Okay? Because the encoder is compressing information. And so that's why if you just directly apply this, you will, so this ZT is something that will follow your prior distribution because that's what the diffusion model is trained to do. But you do not enforce any regularization on the image space because diffusion is done here. So if you run this process, this ZT will be drawn from some distribution here, right? But there is no restriction, no regularization on this one. So you may end up getting some bad ZT, which when decoded will give you some image, which will satisfy your measurements, but it's not a realistic sample. Okay, because there is no prior specified on the image space. The prior is only specified.
Z0 does not happen because stable diffusion produces good
Yes,
images.
yes,
But
but-
possibly the skew.
yes,
skewed
yes,
images.
yes, yes, yes. That's the problem. What?
So you're diffusing not with the score function, you're diffusing with the score function plus the measurement.
Gradient of this, yeah,
And use that to somehow get to ZT.
yes,
So I've gone to ZT somehow.
yeah,
And now that ZT may be a place that I never would have gone to if I just did stable diffusion.
yes,
It's some other weird ZT that lives in the latent space. So I take that.
Yeah.
And I'm gonna forward it all the way to Z capital T and that.
But only if you did this expectation approximation.
yes. Yeah.
Saying if you apply the previous idea and I get some.
Bad ZT, yeah, you'll get some bad ZT,
Yeah,
okay?
it may not.
May not give you,
If I diffuse with the correct score function.
but you never have the correct score function, right? You do not have this is what you are doing. If you just, this is the neural network that you have. If you use only through this, then you are good. You don't have to use this, then you will end up with a good ZT. And if you pass that ZT through the decoder, you'll get a realistic image. But you are not just using that, you are actually,
That red term, exactly, I may not get a good image.
no, then you'll get the good image.
Yeah.
Yeah, then it's not a problem. But you do know this one, so you do some approximation, and that approximation can have some errors, like here, the Jensen's gap or, yeah.
Compounds.
Yes. So now how do you reduce that approximation error? So what we are saying is, so you can again specify some properties on the image space. So the properties of this ZT is already specified by the prior that you have, but the decoded thing, there is no constraint on that. It can be like a bad image, okay? But it will have minimum error with respect to this formula because that's what you are trying to optimize for, okay? But now how do you solve this? So we use this property of this decoder again to specify like what the decoded Z should satisfy. So now suppose you had a good Z. Now if I pass that through the decoder, I'm going to get some image. Now since this is a pre-trained VQVAE or VAE model, so you will get some realistic image. Now if I encode it back, I should ideally get to the same ZT. Okay, so this is some property that we know my VAE satisfies. I just decode to some image, encode it back, I'll get closer to that. So they're like, this is some property I want to enforce. So now this is something that we want to do. So we not only, so when we run the reverse process, this GT will satisfy the prior, but there is no constraint on the image space that it will be a realistic image. So when I decode that, I will get some image which will satisfy my constraints. That means that it will have same, like it will have ideal exactly the same measurements, let's say. But the thing inside, there is no constraint on that. It can be like discontinuous with respect to the background because there is no constraint on that. And the measurement error that I have is only imposed on the known pixels, right? So there may not be any consistency between these two. So that's what the decoder will suffer from.
If you satisfy the prior, just clean.
ZT satisfies, if I do the unconditional generation, then ZT will satisfy the prior of being an image. But I'm not doing unconditional, I'm doing some corrections through this grad log thing, some approximation. So now this ZT may not satisfy the prior that I need.
Is ZT the actual?
So it's just,
Some ZT tilde, which is
so
out of the the jump that you're doing.
Yeah, it's coming out of the correction that I'm adding at every time step. So this is not the true one that I will get if I run the unconditional generation. If I run the unconditional, then I'll get a true sample. But this is some after correction every time step, I will just end up somewhere ZT, which is some ZT variable I got. This is plus some the Jensen's gap through the Jensen's. Yeah. But then when I decode that, I will satisfy the measurement constraints because that's what the DPS trick is doing. I'm forcibly like doing this gradient descent and optimization to make sure that this part aligns with the measurements that we have. This is the measurement. I know only these things. I don't know what's there inside. So I do gradient descent to force the whatever the decoder produces should match with the known part. So that's since I'm doing my optimization explicitly, this constraint will be satisfied. Okay. But the issue is the thing inside this will not be satisfied because there is no guidance to make sure it's a real sample or anything, because the realism is enforced only at this point, not at this point. So what I'm going to do, I'm going to use this property of this encoder decoder. So I just decode that image, the ZT to some image space, that's my this quantity. Then I just merge the unknown parts to copy the unknown parts from the decoded image to the measurement that I have. So this part I don't know. I just take that from my decoded image and paste it here. I create some synthetic image where the boundary here will not be consistent. But if my decoded of ZT is the ground truth image, then when I merge them, I won't lose any information. Now, how do you see that? So here, for example, if you A transpose Y, we know that Y is AX, let's say, plus some noise. So first there is no noise, let's say. So for simplicity, now I can just do A transpose both sides. Now A transpose Y, I can just put it in here. So I have A transpose AX. This X is your X star ground truth. And now here A transpose A minus that plus this will cancel if my X hat is actually the X star. Okay, so this is some constraint it will satisfy if my decoder is actually recovering the true sample. Otherwise, this will have some error. And I want to force this penalty when I'm doing the reverse process. So in addition to doing, so this translates to something following. So the unknown quantity, this is the gradient that we want to compute. So standard DPS will just take this gradient and put it in there. Now, in addition to this, we are forcing some constraints on this encoder decoder to make sure that it's a realistic sample as per the encoder and decoder that we have. Okay. So that's why we take another gradient step towards somewhere such that it becomes like the decoder and the encoder that we have, that also thinks it's a real sample. And so you can actually prove some things in like a simple linear setting. You can show that for any choice of the step size, this helps you to converge towards the optimal solution. If you have the unique solution, you can prove that that's there in the paper. So I'm just going to skip over that. All right, so experimentally, you can show that DPS leads to some bias, and in the latent diffusion case, because of the nonlinear encoder and decoder, and by that bias you can actually remove through the additional correction of the gradient that we proposed. And you can see here, so this is the DPS. So this is the ground truth input image with some blur. This is the ground truth. This is the measurement that we have. So now if you look at DPS, these things are not really resolved. But when you pass this thing through your measurements, you'll still get the same measurements that you have. But the issue is that decoding that too, it won't give you a real image. So the decoder doesn't think that as a real sample. Yeah.
I don't see why this problem is specific to the later. Like, couldn't you add your term? Also,
because the decoder is the problem, right? If you're in the pixel space, then there is no decoder.
I don't see why the decoder is a problem.
Because decoding this will give you this image. And there are many such, so even like if I encode, let's say, if I encode this image, I'm going to get the measurements. If I encode this image and add some noise, I'm also going to get the same measurements. But when I encode them, I'll get like the same latent because the encoder is compressing many images to the same thing. Although some of them are realistic, some of them are unrealistic. So I want to just make sure that when I decode them and I re-encode, I should get back to the same point. So this is some property that is the
not good images and good images the same thing, then how do you even do latent diffusion? Because what if I get I get that latent variable at the end?
Yes.
How do I know I can decode it to a good image or a bad image?
So that's why, so no, that's true. That's why what we are doing, you decode that to some image, but then you take the known part and fuse it in, right?
You're saying that the encoder could map unrealistic images and realistic images the same latent.
Yeah.
Then how could I even do latent diffusion in the first place? What if I get this latent as ZT? How do I decode it?
Yeah. That's the problem with the base generative model. So we cannot go beyond that. All I'm saying is if you are using this latent diffusion for posterior sampling, so you take this ZT, you pass it through the decoder, you will get some realistic images, some unrealistic images here, right? Yeah. So now some of those realistic images, we will have the known pixels exactly aligned, right? And in the unknown region, you can have something that is not consistent with the background that you know here. Okay, and you can also have some images where this portion is exactly consistent with the thing that you know. So these are some of the images that you can get. No, because there is no decoder, right? The decode in the pixel space there is no decoder, so this won't happen there. So this thing is happen because then the prior is specified by ZT. So in the pixel space, you want to satisfy the measurement constraint, and you also want that ZT to come from the prior. So it won't be a realistic image. So that is where it will fail, because the prior will not allow those samples to come. You see that because you are enforcing some. Yes. Now here there is no prior information on the image, so that's why like you are in trouble.
Y is also encoded, right?
Yeah, Y is the measurement that's encoded.
But if I have a ZT, like your example is I have some ZT, and when I
Yes.
decode it,
Yeah.
I get something in the infilling portion.
Yeah.
And then I get the background consistent.
Yeah.
But the border is mismatched.
Yeah. So I just
Why does my latent prior not know this is not a good image?
No, because how would that know? Because the latent prior, when I pass through the decoder, I'm getting some image. So
That ZT corresponds to an image that's not realistic.
Yeah.
I have a prior on ZT.
Yeah, ZT is just coming from somewhere.
yeah,
Not in the critical part of the state space.
yeah. So the additional gradients that you are adding here is
Saying if I just sample stable diffusion all day long from just nothing, I'll never end up with that.
Yeah,
Guaranteed.
yeah.
That's what-
yeah. So because this thing is you are like providing this, adding this additional gradient, which is like moving you to some space in the ZT, which you will never end up if you just use the base generative model.
Yet
Yeah.
true clean image.
Yeah.
I encode that.
Yeah.
That goes to some part of the latent space that if I waited long enough, did rejection sampling.
Yeah, then you will get it.
I
Correct.
would get it.
Yes.
So there's
That's what we are assuming.
So
Yeah.
it's a mismatch between the decoder and
Yes.
the diffusion, like even though
Yeah.
you're maybe doing the right thing.
Yeah.
the latent space, the
Yeah.
decoder just hasn't
Yeah.
hasn't been trained.
Yeah.
realize- Okay.
Yeah. So now using this additional guidance, you can basically fix that issue, and you can prove that having this, you are essentially passing the known information through this decoding and encoding. So now the known part Y is passed through this encoder again, and now you have a new ZT hat. Now you know that this ZT hat is closer to the ground truth image because you just passed this known information through that. Okay, so with this you can just show that, and these are some of the issues that we encountered in the pixel space, like the speed and the resolution. Now those can be resolved. For example, now the gradient is computed in the latent space, and in the latent space you have fewer pixels, so you have fewer partial derivatives, so you can make it much faster. And then you don't need a prior for each task. You can just have a generic prior like stable diffusion, trained on almost anything on the internet, and then you can extract the domain specific prior from it, and you can do that. So these are some of the like real examples that the model has never seen. And we take this image, you mask out this portion, this is the ground truth, and you see that the existing methods, some commercial service providers, at the time we released the paper, they failed to reconstruct that missing portion, whereas our method produced something here, okay, realistic. Similarly, the quality of the things, so here if you mask out one eye, so the existing methods make some distortion or changes the identity of the person. Those things you can better preserve through the encode and decode trick. All right, so here is another example. So if you mask out like one eye, there is a demo of this one on Hugging Face, you can play there as well. So our method produces this eye more realistically compared to the existing methods at the time. Okay, so that concludes the DPS and PSLD that we have. So both the methods use this first order approximation in the pixel space. The DPS uses it in the pixel space, and PSLD does that in the latent space, but both of them use this first order approximation. So now we'll see like what happens if you want to reduce that approximation error. That Jensen's gap we were talking about, can you reduce that error even further? So that's the next paper, so let's discuss that. So recall that in diffusion, in the DPS paper, so we want to compute this unknown quantity. We want to compute this here, but we can only compute the function at the end of the process. And that exactly is written here. So you simulate all the way, compute the function, average them, and that's exactly here, which is expensive. So you do the exchange of expectation, then you can compute the function at the expectation, which is tractable, but it has this Jensen's error. So now another way to interpret that exchange of expectation is through first order Taylor's expansion. So you want to compute this function. We know that this thing is exactly equal to this. Okay. So now if I take the function inside the expectation and do a Taylor's expansion, evaluate this function at the expectation ut bar. Okay, this is a function of two variables. I just try to compute this function of x. I just compute that from function of x naught somewhere in the gradient of the function x naught, then dotted with x minus x naught. And that's the first order approximation I do. And with that first order approximation, you can write it like this. Now the first term here is independent of ut. So this expectation, you can basically pass it all the way to this point. That's where you have ut. So the first term can be taken out. And then this gradient is independent of ut. So the expectation, you can just move it all the way to this. So that's what you have here. So now this expectation is exactly equal to ut bar. So the difference here is 0. So this whole term goes away. So now you have that p of this y given ut is equal to this at ut bar. If you just do a first order Taylor's approximation around the mean, then you can do this approximation. So this is another way to interpret that exchange of expectation that we had. So now the next question is, if we want to reduce the approximation error, why just restrict ourselves to the first order approximation? Why can't we do the second order? So you can just do again like the higher order approximations, and that's essentially what we did in this paper. So now if you want to visualize this exchange of expectation and the approximation error due to this Jensen's gap, you see that for a simple toy example, so this is the expectation of the function, and this is the function of the expectation, and the gap here can be upper bounded by this quantity. And the upper bound here is a dimension d dependent quantity, which means that for d small, the upper bound here is small enough that the exchange of expectation works quite well in realistic setting. Okay, but if d is large, like let's say some MNIST scale, then already the upper bound blows up. That means that this is not really, this approximation error here can be really big. And if you look at even like the stable diffusion scale, dimension is 10 to the 5, so this upper bound basically is super high. Okay, so that's why this Jensen's gap is not really a good thing to do if you are dealing with posterior sampling in high dimension. So now doing the first order error, if you do the second order approximation, we try to reduce that further. Okay. So now to do the second order approximation.
That, like, in both cases.
Yeah.
Really close to zero, you're good.
Yeah.
Obviously, since there are
Yeah.
other places that I could pay to fix this.
So what did you say? I didn't get it.
Is there a step size thing that we?
No, there is no step size. This is for all t, so that's a problem with that one. Yeah. Okay, so now, so to do the second order approximation, so recall that we discussed that if you start from an image, you add some noise to go to xt, which is essentially xt is equal to x0 plus sigma t times epsilon. Okay, given xt, if you want to give your best estimate for x0, then you could use this Tweedy's formula that we discussed in the initial few slides. And Tweedy's estimator gives you this expectation as a function of the score. So this is the exact formula, and you can compute that given only the ut. Now, Tweedy's formula not only gives you the mean, it also gives you this covariance as well, okay, of the terminal state. So you are at this time step. You can compute the end of this process, expected value of ut given little ut. If you start the process from here, run it 100 times, the mean sample that you'll get, you can easily compute using Tweedy's formula. And also the covariance of this thing, you can also compute using Tweedy's formula. That gives you an explanatory formula of this one. And that covariance depends on this del square of log pt. The issue is we only have a neural network to approximate this grad log pt. I don't know what is this second derivative here. So if you want to compute this, you can train another neural network, and then you will have a better estimate of both the mean. So first order you only know, and then if you have another neural network, you can approximate the score. And given the mean and covariance, you can actually assume that the terminal distribution is actually Gaussian, and you can, instead of assuming that as a function of ut only, you can just have a better approximation of the terminal density, and you can do the second order correction. But the issue is that to do the second order correction, you need the covariance, and the covariance needs the Hessian. And we don't have the Hessian, and we don't want to retrain again another Hessian, because this is a very big matrix of 10 to the 5 dimension, right? By 10 to the 5.
I mean, even in the latent space, it's been 1,000 by 10,000.
Yeah. So latent space also, like if it's like 64 by 64, then you just double it, so it's d square again, so it becomes big. Yeah.
But I don't need to put covariance for this exterior problem. I don't need to put variance in reductions.
Yeah, that's essentially what you do. So you don't really. So the dimension of the measurement would be like if you are doing a low, let's say super resolution, the image is of 10 to the 5 dimensional space. That's your image space, X space. Now Y would be some function of this 10 to the 5 dimension thing, which can live in the same space, 10 to the 5 as well. It's just like a blurrier version of it. Yeah. But the good thing is that you can show that if you do a second order expansion of this quantity, we did the first order Taylor's expansion. If you do the second order Taylor's expansion of this function evaluated at ut bar, then that requires some Hessian, some trace of the Hessian. You could just do some calculation we have in the paper. You could show that you don't really need the Hessian. You can just find a lower bound which depends on only the trace of the Hessian. So if you were to compute the Hessian directly, then it is expensive. But you can actually get just the trace of the Hessian using some like Hutchinson's trace estimator, and that is easy to compute. And if you know the trace already, then you can basically implement this equation. So what we want to maximize this thing essentially. Instead of maximize this directly, which depends on the Hessian, we can maximize some lower bound of it. That depends only on the trace of the Hessian. And then we are basically, this is something that is implementable. So that's what we try to do. And the trace of the Hessian can be easily computed. That's through this Hutchinson's trace estimator, which you have in the paper. So essentially, if you want to compute the trace of some matrix, you just take some random projections along some directions. So that's essentially this. So you can think of that as like, you just do this gradient of the function, you just evaluate that, do the Taylor's expansion of this function at zt. Then you have this second derivative, you have some error here. By rearranging the terms, you can move it to this side. And now you have this. Now if I take the epsilon transpose and multiply that both sides, then I'll have the right hand side, I get epsilon transpose del square of epsilon. And if I take the expectation of both sides, then this thing is exactly equal to the trace. Yeah.
Why, is there a reason besides just like it's Gaussian, you take epsilon to be Gaussian? Can you give it any?
No, this thing is true only if epsilon is Gaussian. So this expectation, what?
Which anything zero mean identity covariance.
Yeah, you can pick that. Yeah, that is also fine. Yeah, I just, it's easy to sample. I already get epsilon, so I just do that. Yeah. There is no, you can do that.
So this still doesn't tell me how to compute the trace.
This is it. So this is like a trace thing, and the left hand side is what you can compute. You know a score function, a neural network, which will take some zt as input. Yes, and taking the difference and taking the expression of epsilon, you can compute this trace. Now, if you get this trace, you can compute this loss here, and you can just like do gradient descent or gradient ascent, whatever you're done. So that essentially leads to some algorithms. So I'll just like skip over that for the interest of time. Okay, so let's just skip that part. Okay, so the benefit, as we just discussed, you don't have to recompute. You already have a score function which is approximating the gradient already. You could take the derivative of that, just Jacobian of that one again, and then you'll be able to compute the second derivative, the Hessian. But that requires again order d square compute, which we don't want to do. But if you only use the trace of the Hessian, then you can just do the first order, only the forward pass through the neural network with some epsilon perturbation, and that's easy to compute. So our thing is like much much more efficient compared to computing the Jacobian of the score itself, or even retraining a new neural network to directly approximate the Hessian. Okay. And the benefits of using this second order correction is that you can reduce the the approximation error due to the Jensen's gap. And also you can do fast sampling because the second order approximation tells you to better approximate the curvature of the sample path. And that way, like you can take longer steps, coarser discretization, and that way your approximation error will be like much less. So which is in fact reflected in practice. So if you look at the image here, so this is the eye of this dog here is like visible in our case. Whereas if you look at the prior methods, because it's like a higher order information, high resolution thing, the frequency details and these things are not really captured in PSLD or in DPS or P2L kind of methods. Okay. And there are some quantitative numbers showing exactly the same thing. So another advantage of using this STSL, like the second order correction over the first order, is that it's first of all it's fast and the quality is also better. And if you look at the computationally also, yes. Yeah. That's the advantage, yes. And this is, you see that even in the experiment. So STSL and P2L PSLD, these are all comparable methods of same size. And STSL significantly outperforms the previous methods in terms of quality. And the speed wise, it's also like much faster. It takes just 45 seconds as opposed to like 500 seconds for P2L and PSLD. So it's like 194 seconds. Okay, it just takes 45 seconds. And you don't need too many discrete steps as well, denoising steps. You can just like do 250 steps and you're still good. Because you have higher order information, you can better go through you can approximate the curvature better. So here are some other examples that you can do using this STSL algorithm we discussed. So the general, yes, I have, yeah. But still, yeah. So it's okay. Yeah. Okay, so far we looked at like given in the general inverse problem, we only had access to the input measurements, which was an image, and we wanted to generate the underlying ground truth image. Now, what if we have some additional information with us? For example, if I have this input image and I tell you that the underlying ground truth image is actually a face, and then it will be useful if the input is like extremely blurry. Here you can make out that the ground truth image is actually a face. But if my measurement is extremely corrupted, you can't see almost anything, then having this textual information helps you to reduce some ambiguity. So that is something you can do. And another advantage of doing this is during solving the inverse problem, you can change the text from face to face with red hair. You can do all these things as well. Without change, you will just reconstruct the underlying ground truth image. You can also change it based on the prompt that you have. Okay. And so this is what I was saying, that if you have extreme corruption, your measurement operator is corrupting information significantly, then looking at this, you cannot resolve what the underlying ground truth image is. And here you can see that sometimes it thinks it's a bear, so the uncertainty is very high. But if you provide the text that it's a bear, then you can reduce the ambiguity. Yeah, that's great. Here you can find link to that. So then similarly, so you can do like text guided inversion and text guided editing. So given some input image which is corrupted, like a tiger walking in the jungle, you can invert that and you can also edit using our method. So as a leopard, tiger you can replace with a leopard. You can and also do the inversion at the same time. So the existing methods can do only one thing at a time. They can either invert it to a high resolution image, like given a low res, you can improve the quality of this, but they cannot edit. Or they can only do edit, they cannot invert. Okay, so like you cannot, so here for example, this method can only do edit. So it converts this tiger to a leopard, but it cannot invert because the image here is still corrupted. Okay, this method just copies and pastes here, but here our method, for example, replaces the tiger with a leopard and also inverts at the same time. The background is now more clearer. Yeah, so I think I'll just like finish. So some of the future works here, like if the input image is significantly corrupted, like large number of pixels are missing, then our method takes significantly more number of steps to inpaint those pixels. But if it is lower corruption, those things can be easily handled. So this is some future work that we worked on afterwards. So these are some of the examples we looked at. So we looked at freeform inpainting, then motion blur, super resolution, and then also at the end we briefly discussed like how do you do text guided inversion and editing as well. So I think that I'll finish here. We're out of time, so that's it.